Okay, so next we're going to look at geometric sequences and series, again for IB high level students. Again, we're still in the first part of the syllabus. Here we go, we've got geometric sequence series. We're going to look at the sum of the finite and infinite geometric series as well. Okay, so first thing, again, I guess as before, it's kind of, well, why do we need to know this? In the same way for arithmetic sequences, mathematics is all about finding patterns, explaining the rules behind patterns that we see. This is an example, Sierpinski triangle, which actually is all to do with fractals, and the sizes of the triangles follow a geometric sequence. This actually introduces an entire branch of mathematics all to do with fractal dimensions. So you can actually have a dimension that is maybe not 2 dimensions, not 3 dimensions, but maybe 2.3 dimensions or 2.7 dimensions. So it's an entire branch of mathematics based on fractals. Anyway, as I said, the Sierpinski triangle actually follows a geometric pattern. Okay, so first off, what is a geometric pattern? What is a geometric sequence? Well, very simply, it would be something like this. So here we go. If I've got the numbers, for example, here we go. So I've got the numbers 4, 8, 16, and 32. This follows a geometric sequence because, as you can see, every term, to get to the next term, I times by 2. So if I times by a constant every time, then this gives me a geometric sequence. And as before, there's a simple rule for finding out the nth term of a geometric, and it's this one here. So un, the nth term, is the first term times the common ratio, and then to the power n minus 1. So as an example before, so for my sequence 4, 8, 16, 32, well, my first term for this is 4. R, the common difference, the common ratio, is 2. So I simply put that in there. So say, for example, I wanted to find the fifth term. The fifth term is equal to the first term, which is 4, times by 2 to the power 5 minus 1. So therefore, fifth term is in fact 64. And obviously I could have worked that out from here, but again, that's the method for how to do that. Okay, so there we go. That's how to work out geometric sequence nth term. And again, as before, we're actually able to work out the sum of a geometric sequence, and we call the sum of a geometric sequence this a geometric series when we add the terms together. And this is the formula here. And again, let's try it as before. Say, for example, I wanted the sum of the first 10 terms of the same sequence, and I wanted 10 terms of this. So basically what I actually want to be doing is 4 plus 8 plus 16 all the way up to that 10th term. Okay, so as before, I actually put it all into the formula. So the sum of the first 10 terms, the first term is 4, 1 minus, well, the common difference is 2. I'm going to do it to 10 times, close brackets, all over 1 minus 2. I put that into my calculator, and I'm going to find that the sum of the first 10 terms is 4,092. Okay, and then there's one other thing to look at here. Now, we have something called a sum to infinity, but this only occurs when an r, the common ratio, is between -1 and 1. And when we have r between -1 and 1, this formula actually simplifies, gives us this here, which is the sum to infinity. So as n gets very, very large, it approaches this value here. Now, just to give an example, just to give an example of that one. So for example, if we have the sequence 10 plus 5, again geometric series, 10 plus 5 plus 5 over 2 plus 5 over 4 plus 5 over 8 dot 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 dot. Hopefully you can see that we're basically timesing by half each time. Okay, so that is the common ratio. So therefore my R value, which is half, well, this is between -1 and 1. So I can use the sum to infinity. So the sum to infinity formula that we've just seen is U1 over 1 minus R. Okay, so as before, what this means is as I add and I increase, if I add all these terms all the way up to infinity, I'm actually going to get a specific number. This series here will converge to a particular number. Okay, and let's find out what that number is. So the sum to infinity. So in this particular case here, the sum to infinity is the first term over 1 minus the common difference, the common ratio of a half. So therefore the sum to infinity of this particular series is going to be 20. So if I do 10 plus 5 plus 2.5, etc, 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 I carry on forever, my final answer will be 20. That is the sum to infinity. Okay, and then just the last thing to look at in this particular topic is something called sigma notation. Okay, now sigma notation is just another way of writing a sum of a sequence. So say for example I've got sequence 4, 7, 10, 13. Well, obviously I could write that as an nth term 3n plus 1. So that gives me the terms in the sequence there. Now if I wanted to have a series, i.e. if I wanted to do 4 plus 7 plus 10 plus 13, well, I can actually write that using this notation there, and I can write it as, okay, so this kind of squiggle here basically means sigma, and it basically tells us that we need to add these terms together. And this n equals 1 and 4 at the top, this means I start when n equals 1 and I finish when n equals 4. So I put n equals 1 into here, obviously that's going to give me 4, that's my first term here. I then add the next term, so when n is 2, this is going to give me 7. Well, there you go, that's the second thing I need to add. When n is 3, that's going to give me 10. That's the third thing that I add. And when n equals 4, and that gives me 13. And I stop because that's when it stops there at 4. So sigma notation is just another way of writing the sum of a sequence. And we can use this notation for either arithmetic or for geometric as well.